The Aqualunar Challenge is a $1.6 million international challenge prize focused on making human habitation in space possible by finding ways to utilize water found on the Moon. The Moon contains significant amounts of water ice, particularly in permanently shadowed craters at its poles. Around its south pole, an estimated 5.6% of the soil, or regolith, is water frozen as ice. The Aqualunar Challenge set innovators the task of developing technologies to harvest and purify this water ice found in the lunar soil. Isle Utilities' Caroline Wadsworth worked on the Aqualunar Challenge to bring together scientists, engineers, and innovators to create systems to efficiently extract and treat lunar water. 10 cutting-edge teams were named as the finalists in June 2024 and awarded £30,000 each to develop their technologies further. Let's hear from Caroline and some of the finalists now.
Caroline, thank you so much for coming on Water Action Platform.
It's a pleasure.
What was the purpose of Aqualunar? Give us in a nutshell what Aqualunar is all about.
Super. So the Aqualunar Challenge is a £1.2 million challenge prize fund, and the aim was to find a series of solutions that would be able to purify 1 litre of water an hour on the Moon. There are pockets of water on the Moon. They're all on the dark side of the Moon, so you can already see that there are some challenges coming into how these solutions might work. But there are ice pockets that have obviously contain water, but also a number of different contaminants, and regolith, which is really the sandy kind of surface of the Moon, and it's very coarse and causes lots of problems in that purification process. And the aim was to create, if you could create 1 litre an hour, in theory, that's just about sufficient to be able to allow humans to live for longer in space. So that could either be on the surface of the Moon, and that would allow them to have vegetables and grow different kind of crops that would allow them to eat and live there, but also as a source of water for them to drink, and as a source of fuel to allow them to go further into space. Oh. And actually, water is one of the heaviest elements or items that they take up to space. And a lot of the cost of exploring space is dictated by the weight of the space rocket that goes up. So the more you can reduce that weight, the cheaper that space exploration becomes. And obviously, the longer they can stay there. So the greater the reality or the chances of getting to Mars become if we can have a source of water actually out there in space.
Much better chances. So it's water for human consumption, for food production, and for fuel. I didn't realise that bit. Okay, that's really interesting.
Yeah.
Now that we're at the end of the Aqualunar Challenge, or almost at the end of it, what are the main outcomes that you've seen emerge from the challenge taking place?
We have selected 3 winners. So there's a winner, a first runner-up, and a second runner-up. But actually, all of the entrants were amazing. So I think the main outcome has been an accelerated journey for those participants through that challenge. They not only got to mix with each other and bounce off each other, they got access to a range of experts, whether from within Isle, from a water perspective, or our partner organisation, Exotopic, who provided more space-based expertise. So they've now accelerated through their journey of coming in at a really very, very early stage, so very immature solutions, through to still relatively immature solutions, but they've moved on in leaps and bounds, and they've had access to test facilities, for example, that they would never ordinarily have had.
When it comes to sort of implications or applications in the real world, what's the value of the outcomes that they've had, those introductions to the space community and the water industry?
Well, huge value to that. So the transferability from space to the terrestrial applications, it is massive. And actually, when you look at the reality of the space market versus the terrestrial markets, the terrestrial markets are a much nearer term opportunity. So if they want to stay afloat and be around for long enough to actually take advantage of those space markets, they need to really grab hold of these terrestrial-based market opportunities. So we've been able to introduce them directly to water companies that could potentially be deploying these. but also a range of other and potential end users, because the applications are so broad of this kind of solution that they're developing. And we've also been able to advise them of the type of solutions that they're competing against, so they understand what they need to displace or what their USP is against those. Just huge opportunities for them moving forwards. And there's been an enormous amount of interest from the utilities in the UK.
That's awesome. Were there any surprises in it for you, either welcome surprises or unwelcome surprises?
No unwelcome surprises. I think the biggest surprise has actually been just the amazing thought processes that the entrants have gone through to get from this very early stage, quite high brief in terms of the problem statement for the challenge, to where they've ended up now with solutions that are feasible. They are technically proven, at least on a small scale, at a laboratory scale. And the potential for them is massive. But I think one of the things that's been most surprising was the feel of the cohort. So it's not about the technology. It is about how well that group of participants work together in a competitive environment, but they learn to overcome those, share enough information to allow themselves to still remain competitive, but created that real peer group that supported each other and really celebrated at the end when not all of them did get through to that final podium, but all succeeded through that process. So I think that was probably the most exciting or interesting or beneficial output from my perspective.
Fantastic. Thank you very much. That's a great introduction to Aqualunar. And now we're going to hear 3 of the teams presenting their tech.
I'm Sean Fletcher. I'm a first-year PhD student at the University of Glasgow. We have done some research in how to use ultrasound to attack pollutants that would be in water domestically. And it just seems like a very interesting step to kind of take that to the next level and look at kind of wider applications. That's something that this challenge offers. And also the fantastic non-financial support that gets offered as part of this challenge, to be able to consult with these experts who are really leading the field. We do a lot of work in electrochemistry, and one of the things we've studied is how that works in low gravity environments. And it's kind of fascinating to see the differences between things that happen here on Earth versus how they might happen in space with low temperatures, low gravity, extreme conditions. And it's an absolutely fascinating challenge trying to kind of develop adaptations for that technology to work up in space or on the moon or on Mars or further afield than that.
My name is Abigail Charlton. Our project is called TIDAR. To think about the fact that we could actually create a technology to make water on the moon is just amazing. The idea that we can be a part of the step towards some sort of lunar economy in itself is more than enough to just make it worth it. It's been really, really amazing to chat with some of the other folk and to learn things from the panel as well. They were super interesting. Definitely excited about the future. Come next March, whether we get that prize or not, we will definitely be looking to innovate in the space environment because there's just so much potential there, and just a small team like NASCENT can really branch out into something huge, I think.
My name's Philip Baldock. I am trained at the university level as a physicist and materials scientist, but really my passion is space. And that's really what's brought me to this Aqualunar challenge. Our concept, which we're calling Ganymede's Chalice, is basically to use a solar concentrator to take sunlight and focus it in to a single spot where we preferentially evaporate one by one each component of the lunar ice regolith mix. I'm really excited by what I think we might be able to achieve with native European technologies and with cooperation locally. I think it has a lot of potential really to make some interesting new ideas. I'm really glad to be part of it.
These 3 finalists are developing very diverse technologies. In Lunar's sonic system, melted ice is pre-filtered to remove particles, then processed in a sonoreactor where ultrasound breaks down the volatile compounds and flocculates the lunar dust. Final polishing is done via lunar regolith filtration. TIDAR employs UV light from LEDs to activate a titania catalyst and diamond electrodes, which are robust enough to withstand the abrasive lunar soil and the G-forces experienced during launch. It rapidly breaks down both inorganics and organics in the lunar soil to create drinking water and rocket fuel. Ganymede's chalice is a solar concentrator, a curved mirror to focus the sun's rays on an air-locked crucible where lunar ice is placed by a small automated crane. The heat from the concentrated rays boils the ice components one by one, and the system stores each component separately, finally condensing potable water.